Hello, welcome back to our channel, and we are going to use a spice simulator which helps us to draw the schematic and simulate and analyze the performance of a circuit. So we are going to understand the circuit, its behavior. So is basically a oscillator circuit, namely Hartley oscillator. We have already seen the theory and your principle of operation of this circuit in one of our previous modules. So if you are new to our channel or to this module, we encourage you to refer back to that module and then come again to understand the analysis of this circuit through simulations. So what we are going to do, I have created this circuit here and I'm going to simulate this circuit to see whether I get a sustained oscillation from this circuit at a desired frequency of oscillation. So let us understand one by one each of these components. So here is this transistor that I have chosen, that is 2N2222. So if I right click this transistor, I see it's the manufacturer name here, and then I also see it's an NPN transistor with the VCEO, that is the open circuit voltage between collector and emitter pin. This maximum 30 voltage before the breakdown can occur, and the collector current this transistor can withstand maximum is 800 milliamps. Here you can pick up the transistor, and you have variety of transistors that you can actually choose. And this transistor that I have chosen is a small signal amplifier transistor with the beta factor of about 200. That's the DC current gain. So if you actually remove this part from the circuit, which is L1, L2, and C4, and you focus on only this part right here, so which is transistor Q1, collector resistance, emitter resistance, and this R1 and R2, and three capacitors, C1, C2, and C3, of course, along with the DC voltage source. So this part of the circuit is essentially a small signal amplifier. Okay, and we have covered this part also in our one of the module using the spice. So again, you can always refer back to that mod. So I have used the 10-volt DC voltage source to provide the power to the circuit. R1 and R2 is the voltage division biasing scheme that I have used to set the DC operating point of this circuit, that is the VB, and the voltage at the base pin, and the voltage at the emitter pin. So here it will be a 0.7 volt voltage drop between VB and VE, between the base pin and the emitter pin. That is the voltage difference between the base and emitter. And you have this resistance RE in the emitter, you have resistance R3 in the collector. So these two resistors, as I said, providing the DC bias to the circuit to set the operating point, and I want to use this biasing in such a way that it says it gives the operating point in the middle of a DC load line. Okay, and therefore I can use it as the uh, voltage amplifier or a current amplifier. So basically the circuit is biased in a common emitter mode. Register RC is actually the register R3 here, which is providing the gain to the transistor. So without the emitter resistance, the gain of the circuit is transconductance of the transistor Q1 multiplied by the value of this resistor GM times RC. Here it is R3 now. Otherwise, we use the resistor RE in the circuit, and in that case, your gain of the transistor, gain of the circuit when RE is included is the ratio of R3 divided by RE, which is RC. You can call it R3 or RC divided by RE. And there'll be a negative sign here because it's an inverting amplifier. The value of the C1 and the C2, which are the coupling capacitors of each 1 microfarad is chosen. The values are chosen in such a way that at the frequency of operation, these capacitors provide low reactances or low impedances. Essentially, they act as a short circuit for the AC signal so that the alternating signal at the input pin gets coupled to the circuit here at the input side. And from here, the C2 acts as a short circuit at the desired frequency of operation so that the AC signal at the collector pin gets coupled to the load that we connect at the output. Here is the output. C3 is a bypass capacitor. So at the DC, it acts as an open circuit. So as if it is not there in the circuit. But at the very high frequency, it acts as a short. The reactance is extremely small so that the RE gets bypassed from the circuit. And that's how when RE is not there, your gain improves. So gain is then decided by GM times R3, as I said before. But for the other frequency range between, let's say, the way you design the circuit in such a way that you have a minimum frequency and the maximum frequency where the gain is flat. So in that case, RE can be there, and C3's role at DC it acts as short, and at very high frequency it acts as an open circuit. That's it. So this circuit is acting as an amplifier, inverting amplifier. Now, what I am doing, I have removed the load, which is a resistive load assumption, and instead I have put up this network composed of L1, L2 in series together. In between, the common point is connected to the ground, and you have there is a capacitor C4. And the values are chosen in such a way that 2.2 micron each for L1 and L2 and 47 nanofarad for C4. So output of the amplifier is given or is becoming an input to this network, which is the tank circuit formed by L1, L2 and C4, which is here, and then output of this tank network is being fed back from here to back to the amplifier input. So you don't really have any external input to the circuit. In case of amplifier, you don't have this network for assumption, and then you apply AC input here to simulate the transient response, AC response, etc. We have seen that in earlier lectures, but now we are building an oscillator. So again, output of the amplifier is input to the feedback network composed of L1, L2, and C4, and output of the feedback network becomes an input to the amplifier. So it's a closed loop circuit. It's a closed loop with the gain, closed loop gain given by A multiplied by the beta. So A is the gain of the amplifier, beta is the gain of the feedback network. So this is basically this network provides the gain to the signal, that is the amplifier, and this network attenuates the signal, and that's why there is opposite terms used. Here it's called as gain, here it's called as attenuation. Now we have to satisfy the two criteria of oscillations in order to sustain the oscillation in the circuit. So this is a linear or harmonic oscillation circuit that we are going to see. It will produce a sustained sinusoidal waveform at the output, and we will also simulate its frequency spectrum to see how the fast Fourier transform of the sinusoidal output looks like. We'll see that. So Of course, the frequency of oscillation is determined by these components, which are the passive components L1, L2, and C4. And the formula is F equals to 1 over 2 pi square root LC, where L is the combined inductance or the sum of two inductors, L1 plus L2. And if there is any mutual inductance between them, so there is also plus minus 2M term gets added to the inductors. And you have this capacitor C. So F equals to 1 over 2 pi square root LC is the frequency of oscillation. So based on the values I have chosen, the frequency of oscillation for this circuit is set to be around 380 kilohertz. I repeat, 380 kilohertz, and we'll see that. Now, that's the resonant frequency offered by the tank. So now I need to satisfy the two conditions for oscillation produced by this circuit. One is the loop gain, which is the product of gain of the amplifier A multiplied by the beta factor or attenuation factor or the gain of the feedback network beta. So A times beta has to be greater than equal to 1. That is my first criteria. And second criteria is the loop, the phase of the loop gain. Again, the loop gain is the product of A multiplied by beta. So the phase of that loop gain around the loop should be exactly 0 degree or multiples of 2 pi radians, such as 360 degree, 720 degree, and so on and so forth. So if I manage to satisfy these two conditions, I will get the oscillation at the output pin, a pure sinusoidal waveform. So how much is the gain A of this amplifier? Again, it's set by the ratio of resistor R3 and RE. So R3 chosen 12K, RE chosen 1K. So gain is about 12. So A times beta is has to be greater than equal to 1 of the oscillation condition. And now my A is 12. So A times beta, let's say equal to 1. It means beta will be then 1 over 12, right? Again, I repeat, A is 12 and I want A times beta equal to 1 minimum. So beta then will be 1 over A and A is 12. So beta will be 1 over 12. And that is why this feedback network acts as an attenuator. It basically attenuates the output signal. So by a factor of 12, it is attenuating the output signal from this node. And then the attenuated output is being fed back in phase with the input signal. Okay, in phase. So as I said, this is an inverting amplifier which provides the phase shift at the output of 180 degree. Output will be 180 degree phase shifted with respect to input, and the remaining 180 degree phase shift will be provided or has to be provided by this feedback network. So 180 degree plus 180 degree, total 360 degree phase shift around the loop I can expect. Okay, so I have done the operating point analysis for this circuit. The values accordingly have been chosen to set the correct operating point, such as the values of R1, R2, R3, and RE, and even the capacitance values, as I explained before. Okay, and the frequency of oscillation, the resonant frequency of the tank is about 380 kilohertz. So before that, we would still like to run the DC operating point analysis just to understand what is the operating point of this circuit. So what we'll do is, for a moment, disable this, right click on this transient analysis, and here I'll put this sign to disable this analysis. So this analysis is not active anymore. Instead, I would do one thing. I click here and now I clicked here, and here I will write dot op, means perform the DC operating point of this analysis, and then I will save, click run to simulate, and look at this. Now I have got this voltages and currents into the circuit. So let us understand one by one what is the output volt. DC voltage is 10 volt. Output voltage is about approximately 0 volt. Yeah, it's minus 22. Voltage at the collector pin of the transistor is about 0.88. Base voltage is at 1.41, and then 1.41 minus the VBE, that is 0.7, will be the voltage at VE. So let us check what is the voltage here, 0.7. So obviously 1.4 minus 0.7 will be 0.7 approximately. Okay, and then look at this current. The collector current is about 0.7 milliampere. The base current is 7 microampere. And this is how it goes, right? Yeah. Uh, and then that's how you got this one. So let us assume that now we finish this operating point, and now let me enable this one. So let us enable this, that is dot trans, and I will click the simulation button, that I will hit simulation, and we are running the transient analysis. Look at this now. So I'm running the transient analysis for 50 millisecond time period. I look at this sustaining oscillations. The amplitude initially growing. It starts from the 0 volt right here on the y-axis, and at around 9 milliseconds. So my startup time in the circuit is 9 millisecond approximately right here. So it takes me 9 millisecond. It takes my circuit approximately 9 millisecond to start the oscillation, and the oscillatory amplitude is growing, 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 and here you got the steady state oscillation. Look at this. You got this steady state oscillation. So why not? How about we'll run it maybe a little bit more? Of course, we've got this. You see here, we got this steady state oscillation. Exactly. So you can increase the time, stop time also. Without the startup condition, let us check how the circuit behaves. So let us click and look at this. It's starting approximately at 0 millisecond, and the oscillations are growing, growing, and you still have like growing amplitude. Right. So approximately at about 30 millisecond, you get the sustained oscillation, right? You get the sustained oscillation, but it's, I think it's still growing. So you just zoom in the portion and look at this sinusoidal waveform. You got this waveform here. There is a little bit jitter here. So if you zoom in that portion, so this is called as, this is, jitter is the phenomena that affects the periodicity of your sinusoidal waveform, of your signal actually. So jitter is the term that indicates how much is your periodicity of the waveform is affected. So right here you've got this one. So if you right click here and you view here and say that you want to put some marker, and then you actually mark data points Oh, yeah, this is like you're marking the data points. Here you can plot different traces. So view again, and okay, so you have some, let's say right click on this here. And you can then click the cursor, first cursor. So take this cursor in the middle here. And again, you see this Hartley oscillator. So horizontal is like 45.87 and then vertical is 2.6 volt. So I delete it. Again, I right click and attach the cursor, or instead of first, I will say first and second. And then I got this two cursors here. So first cursor, I keep it here. And the second cursor, I keep it here, for example. And from that, you can see now this two cursor frequency is about 340 kilohertz, 347. So theoretically, I said I am calculating 380 kilohertz something. So 340 kilohertz are closely approximating that. So this is how you can actually see that. Okay. Now, excuse me. Now let's do one thing. We would add our what we are going to do now. We would add the startup command in the transient analysis. Right click here, and I will just type space and then start up. That's the command. Okay, maybe a little bit increase the time to 50, then maybe 60 millisecond. Why I'm taking 60 millisecond? Because my frequency is 380 of 350 kilohertz. Right. So I will then click the simulation and will check if I have this signal, and then I will zoom to fit and look at this. From zero, it's starting, and then at approximately 9 millisecond, I got this steady state oscillation, unlike the previous case. So you can see that it is still a little bit growing here. It is growing, so it is like overdamped case, right? And then we'll see at what time it reaches the steady state. So we have to wait for certain time until it really reaches and the oscillation amplitude stabilizes. So it's 24 millisecond, but now here it's 50 milliseconds. So we'll again have to wait for a while until it reaches the 50 millisecond, and then we'll zoom in to the specific portion to get the clear side view. Here you see that simulation time is 24 millisecond, which is covered. 40% of the transient analysis done. Speed is 0 second per second. Enter is 3 fills. Okay, so there is some command here. Okay, so while it goes to the end, we will just wait for a while. So you can see that we started with a growing amplitude, and then somewhere from this area, we have reached the constant amplitude, right? So maybe we can just choose to zoom in this portion and zoom in more right here, and maybe right click and view, and mark data points. We don't want to mark that. So you got this. And I have already shown you how to calculate the frequency. Just all you need to do is right click on this symbol and attach cursor first and second. Click OK, and then first cursor goes here, the second cursor goes here. So we are calculating one time period from this point to this peak, one same peak. So it's about 340 kilohertz, 350 kilohertz. That's it. Now, what I can do is add a plot pane here, and I want to see the FFT, fast Fourier transform of the generated sinusoidal waveform. So I will just right click on the empty plot pane, and then I will see what I can do. So view, and then click here FFT. And then I choose this output waveform because that's the voltage I want to see the Fourier components of. So the Fourier components are normalized to correspond to the time domain RMS amplitude. I will see that some parameters here, number of data point samples in time is about 262,000. Start time, they use extent of simulation data, number of points 3, window function none. I can just choose if I want, but the DC component is removed before windowing, so I'm keeping it as it is. Click OK. And here you have this fast Fourier transform of this signal. You can see now, and look at this wave, this peak uh, voltage or peak power actually. So the peak power is about 0 dBm, touching to 0 dB, not the 0 dBm, 0 dB. So if I right click here, I can choose the logarithmic scale, linear scale. It's the Bode plot actually, maybe linear scale. So if I choose linear scale, I have this kind of, so it's about 1.1 volt. Let's look at this impulse. I will just then again go to decibel and click OK. And that's how I get this. So here is my career. Here is my career. And if I choose to have the zoom in view of this, so here you can see that this is a kind away from the carrier to the left or right. I have a flicker noise. It's a phase noise of the oscillator actually. So we can actually add to one. So look at this frequency of oscillation is right here in the center, isn't it? Right here in the center, right here is about 350 kilohertz, and then from that carrier in the at a distance of let's say 10 kilohertz, I can measure the phase noise. So it's like so not from this scale, you need to have some calculation here. So we'll do that later maybe, but now you can actually see that. Okay, so you got to understand how we can actually do the oscillation circuit design, how we can actually run the analysis, how to simulate the circuit. So hope you like this video. If you did so, share with others, click like button, put some comments, and till then stay tuned for more engaging contents like this. Till then, wish you happy learning.